Can physics put you to sleep? Let's dive into real paradoxes that bend your mind and ease you into slumber. Subscribe for more dreamlike puzzles. Mpemba Paradox. Imagine two identical containers of water, one filled with hot water and the other with cold water. You place both in a freezer at the same time. Surprisingly, the hot water sometimes freezes faster than the cold water. This seems to go against common sense because you would think the colder water is already closer to freezing and should reach ice sooner. The effect was named after Tanzanian student Erasto Mpemba, who in 1963 noticed that hot ice cream mix froze faster than a cooler batch. Yet people as far back as Aristotle and René Descartes remarked on hot water freezing quickly under some conditions. Scientists have since explored many factors that can make this happen. Hot water can lose more mass through evaporation, reducing the amount that needs to freeze. The warmer liquid can also promote stronger currents inside the container, distributing cooler temperatures more evenly. Dissolved gases in cold water may slow freezing, while hot water often has fewer gases. The shape and material of the container, how the freezer air flows around it, and even subtle differences in supercooling all play roles. No single explanation covers every case, and the Mpemba paradox remains an active area of research. Its study shows how a simple everyday observation can reveal complex interactions between heat transfer, fluid motion, and material properties. By questioning our assumptions about hot and cold, we gain richer insight into the real behavior of water and the hidden subtleties of nature. Black hole information paradox. Imagine a region of space so dense that nothing, not even light, can escape its pull. This is a black hole. Now picture throwing a book into the black hole. The pages, the letters, the ideas inside the book all seem to vanish forever behind the event horizon. Yet, in quantum physics, information cannot be destroyed. In 1974, Stephen Hawking showed that black holes slowly emit what we now call Hawking radiation, a random stream of particles. Over time, the black hole can evaporate completely, leaving only that random radiation. Where did the information in the book go? If it disappeared, that would break a fundamental rule of quantum mechanics. This clash was first highlighted in the 1970s and became known as the information paradox. In response, Gerard T. Hooft and Leonard Susskind proposed in the early 1990s that all the information about what falls into a black hole is somehow stored at its surface like a hologram. This idea, called the holographic principle, suggests our three-dimensional world may itself be a projection of information on a distant boundary. In 1997, Juan Maldacena gave a precise realization of this in a mathematical model known as CF duality, showing how a quantum theory without gravity on the boundary can fully describe gravity inside. While the full resolution for realistic black holes remains an active research question, the paradox has driven major advances in our understanding of quantum gravity, space-time, and the deep link between information and the fabric of the universe. Imagine a race between the swift hero Achilles and a slow tortoise. Achilles lets the tortoise start a little way ahead. In the first moment, Achilles runs to where the tortoise began, but by then the tortoise has moved forward. Next, Achilles runs to that new spot, and again the tortoise has crept on. This pattern can repeat forever. Each time Achilles reaches the tortoise's last position, the tortoise is a bit further ahead. It seems Achilles would need to finish infinitely many tiny steps and thus could never catch up. In real life, he overtakes the tortoise easily, so what's going on? Zeno's puzzle shows how slicing an action into endless pieces can trick our minds. Mathematicians centuries later used the idea of infinite series, sums of infinite shrinking numbers, to prove that all those tiny steps still add up to a finite distance and time. Yet Zeno's original thought experiment reminds us how intuition can fail when we stretch familiar ideas to their limits. Imagine you want to walk from one side of the room to the other. First, you must cover half the distance. Then you must cover half of what remains. Then half of what is left after that. You keep doing this forever. Half, half again, half again, half again, without end. It seems you would never reach the far wall because there are always more half steps to take. This puzzle dates back to about 450 BC, when the Greek philosopher Zeno of Elea used it to challenge our ideas of motion and space. In everyday life, you clearly cross the room in a few steps, yet Zeno's argument slices the journey into an infinite number of ever smaller pieces, making completion seem impossible. Centuries later, Aristotle described Zeno's paradox and wrestled with its implications. Finally, in the 17th century, mathematicians like Newton and Leibniz developed calculus and infinite series. They showed that an infinite sum of shrinking distances can add up to a finite total. In other words, although there are infinitely many half steps, their lengths get so small that together they equal exactly the room's width. Zeno's dichotomy remains a powerful reminder that our intuitions about going from here to there can break down when we push them to infinity. It encourages us to look deeper at how space, time, and numbers really work together. Maxwell's demon. Imagine two rooms connected by a small door and filled with gas. A tiny clever creature, Maxwell's demon, watches every gas particle. When a fast, hot particle nears the door, the demon opens it and lets that particle into room A. When a slow, cool particle approaches, the demon opens the door to send it into room B. Over time, room A grows warmer and room B grows cooler, even though no extra heat was added. This seems to break the second law of thermodynamics, which says heat naturally flows from hot to cold, never the other way around. In everyday life, you don't see cold coffee warming itself by pulling heat from a warm cup of tea. Yet Maxwell's thought experiment, proposed by James Clerk Maxwell in 1867, suggests a way to reverse that flow using information. More than 60 years later, physicist Leo Szilard analyzed this idea in 1929 and showed that the demon needs to measure each particle's speed to decide when to open the door. Gathering that information and later erasing it from the demon's memory costs energy. In 1961, Rolf Landauer made this precise, demonstrating that erasing information always generates heat. Other restores the second law that demon's actions end up costing at least as much energy as the heat it seems to create. Maxwell's demon remains a powerful illustration of how information and physical energy are deeply connected. It helps spark the fields of information theory and quantum computing, and it reminds us that knowing more about a system can itself have a physical price. This authentic puzzle blends 19th century insight with modern understanding, showing that nature's rules hold firm once we account for all the cost. Loschmidt's reversibility. Imagine a set of tiny balls bouncing around inside a box, each one following the same simple rules whether time moves forward or backward. If you could pause the motion and reverse every ball's speed and direction exactly, they would retrace their paths and return to their starting spots. Yet, in real life, we never see a broken cup reassemble itself or mixed cream separate from coffee. In 1876, Austrian scientist Johann Loschmidt pointed out this clash between the time-reversible laws of motion and the one-way flow of heat and mixing that we observe. Classical mechanics says particles don't care if time runs forward or backward, but everyday experience and the second law of thermodynamics says disorder always. How can these be reconciled? In the late 19th century, Ludwig Boltzmann showed that irreversible behavior is a matter of probability. With trillions of particles, almost every possible arrangement of speeds and positions leads toward more disorder rather than less. While reversing every single particle is allowed in principle, the chance of all of them doing so at once is so vanishingly small that it never happens in practice. Loschmidt's challenge and Boltzmann's response lie at the heart of statistical mechanics. They teach us that the arrow of time, why things age, mix, and cool, arises not from a breakdown of fundamental laws, but from the overwhelming likelihood of moving toward disorder in large systems. This authentic insight connects the microscopic reversibility of physics to the macroscopic world we live in. Olbers Paradox. Imagine standing under a clear night sky filled with stars. If the universe stretches out forever and contains an infinite number of stars, then in every direction you look, there should be a star shining right at you. The sky ought to glow as brightly as the surface of the sun, yet instead you see darkness punctuated by points of light. This question was first posed in the early 19th century by the German astronomer Heinrich Olbers. He asked why the night sky is dark if distant stars are everywhere. In his time, most people thought the universe was static and unchanging, so Olbers' reasoning seemed sound. He wondered whether dust or gas might block distant starlight, but any absorbing material would eventually heat up and glow itself, so that solution fell short. In the 20th century, astronomers solved the mystery by realizing that the universe is not static and infinite in age. It began in a hot, dense state about 14 billion years ago and has been expanding ever since. Light from the most distant stars and galaxies has been stretched to longer, less energetic wavelengths by this expansion, a process called redshift. Many stars simply lie too far away for their light to have reached us, yet Olbers' paradox highlights how a simple question about darkness led to profound discoveries about cosmology. It shows that observing the night sky can reveal the universe's age, its dynamic expansion, and the deep connection between light and space. This authentic puzzle reminds us that sometimes a question as ordinary as why is it dark at night can open a window onto the cosmos. Roger's cat. Imagine a sealed box containing a cat, a tiny amount of radioactive material, a detector, and a vial of poison. If the atom decays, the detector triggers and the poison is released, killing the cat. If the atom does not decay, the cat remains alive. According to quantum theory, the atom exists in a superposition of decayed and not decayed until someone looks. So the cat is both alive and dead at the same time. Erwin Schrödinger proposed this thought experiment in 1935 to show that applying quantum rules to everyday objects leads to an absurd picture. In the microscopic realm, particles can be in many states at once until measured, but we never see cats that are both alive and dead. This paradox highlights the gap between the strange behavior of atoms and the solid reality we experience. Physicists now describe how interactions with the surrounding environment cause decoherence, which rapidly forces the system into one outcome or the other without anyone opening the box. Yet the fundamental question remains: how do possibilities collapse into a single reality? This authentic puzzle drives at the heart of what a measurement really is in quantum mechanics. As you picture the cat quietly poised between life and death, let your mind settle on the mystery and drift gently onward. Einstein Podolsky Rosen Paradox. Imagine two particles created together so that their properties remain linked even when they move far apart. If you measure one particle, you instantly know the result you will get for the other particle, no matter how distant it is. Albert Einstein and his colleagues Boris Podolsky and Nathan Rosen described this puzzle in 1935 to show that quantum theory seems incomplete. They thought something hidden must carry information between the particles faster than light, which should be impossible according to relativity. Experiments starting in the 1970s tested this idea using famous inequalities by John Bell. They showed that no hidden signals can explain the results. Entangled particles truly behave as if they share a single combined state that only becomes defined when we look. Yet, no usable message can travel faster than light this way because the outcome is random until measured. This paradox remains authentic and deeply informative because it sits at the heart of quantum mechanics. It has led to modern applications in secure communication and quantum computing, while reminding us that nature can link distant objects in ways that defy our everyday ideas of cause and effect. Twin paradox. Imagine identical twins named Alice and Bob. Alice stays on Earth while Bob travels in a spaceship at very high speed, close to the speed of light. According to Einstein's theory of stationary relativity, moving clocks tick more slowly than stationary ones. From Alice's point of view, Bob's clock on the fast moving ship runs slower, so he should age less. But from Bob's view, he is at rest and sees Alice moving, so he might expect her clock to run slower and that she should age less. Which twin ends up younger when Bob returns to Earth? Einstein's resolution involves acceleration and changing reference frames. Bob's journey is not symmetrical. He must speed up, turn around, and slow down to come home, while Alice stays in one inertial frame. During the turnaround, Bob switches frames, and that break in symmetry means that when he returns, the calculations show he has aged less than Alice. This paradox was first described in 1905 and later formalized with clear mathematics. In 1971, physicists Joseph Huffely and Richard Keating flew atomic clocks around the world on commercial airliners. When they compared the flown clocks to ones left on the ground, the moving clocks indeed showed slightly less elapsed time, matching Einstein's predictions. Modern GPS satellites also account for these effects every day to provide accurate positioning. The twin paradox teaches us that time is not absolute but depends on motion and acceleration. It remains an authentic demonstration of relativity's surprising consequences, rooted in both theory and real experiments. Bootstrap Paradox. Imagine a time traveler who goes back to the year 1610 and meets William Shakespeare. The traveler gives Shakespeare a printed copy of Hamlet. Shakespeare studies the play, copies it word for word, and publishes it under his own name. Centuries later, the traveler finds the published book, takes it back in time, and hands it to Shakespeare again. Who actually wrote Hamlet? This puzzle highlights a causal loop with no clear origin. The play seems to exist without ever being written by anyone. It loops forever between the future and the past. The idea of objects or information appearing from nowhere in a time loop was discussed by science fiction authors and philosophers more than a century ago. In physics, solutions to Einstein's equations of general relativity, found by Kurt Gödel in 1949, allow for closed time-like curves, paths through space-time that return to their own past. Such solutions suggest time travel might be possible in theory, but they also open the door to paradoxes like this one. To resolve the loop, some physicists invoke the Novikov self-consistency principle, which says events in a time loop must be self-consistent. Whatever happens in the loop can never create a contradiction. Applied here, that principle implies someone, perhaps an unknown author, must have first written Hamlet, and the loop simply preserves that original work. Yet the paradox still pushes us to ask how causality and information work when time itself becomes flexible. The Bootstrap Paradox remains an authentic challenge because it combines real solutions in general relativity with deep questions about cause and effect. It reminds us that if time travel were possible, our usual sense of first cause might break down entirely. Grandfather Paradox. Imagine you built a time machine and travel back to a day before your grandfather met your grandmother. If you prevent their meeting, your parent was never born, and therefore you could not exist to go back and stop them. Yet if you never existed, you could not have stopped their meeting, so they would meet and you would be born after all. This loop creates a clear contradiction. Philosophers and writers have explored this idea since at least the mid-20th century. The name Grandfather Paradox became popular in science fiction and philosophical discussions in the 1970s. In physics, solutions to Einstein's equations sometimes allow closed time-like curves, paths through space-time that return to an earlier moment. So general relativity, in principle, permits scenarios that lead to this paradox. Several resolutions have been proposed. One is the Novikov self-consistency principle, which says that any actions taken by a time traveler must be part of history all along, so paradoxical changes never occur. In this view, if you tried to stop your grandparents, something would always prevent your action. Your gun might jam, or someone else intervenes, ensuring history remains consistent. Another idea is the many worlds interpretation of quantum mechanics, which suggests each decision creates a branching universe. Preventing your grandparents in one branch simply births a reality where you do not exist, while you still exist in the original branch. The grandfather paradox remains a powerful way to question how cause and effect would work if time itself were flexible. It shows that even without equations, the very idea of changing the past can lead to genuine logical puzzles, and it continues to guide serious debates in physics and philosophy about whether time travel could ever be possible. Wave-particle duality. Light and tiny bits of matter can behave like waves and like particles at the same time. In the early 19th century, Thomas Young shone light through two narrow slits and saw a pattern of bright and dark bands on a screen, just like ripples of water overlapping. This proved that light spreads out and interferes like a wave. A century later, Albert Einstein explained the photoelectric effect by treating light as packets of energy called photons behaving like particles. Electrons and atoms later showed the same dual nature in experiments that send single particles one by one through two slits and still build up an interference pattern over time. This means each particle somehow goes through both slits and interferes with itself until it is detected at one spot on the screen. The mystery prompted Louis de Broglie to suggest that matter has a wavelength, and later led to the development of quantum mechanics by Schrödinger and Heisenberg in the 1026. Today, electron microscopes and semiconductor devices use this wave-particle duality to produce images and power modern electronics. Wave-particle duality reminds us that at the smallest scales, our everyday ideas of solid particles and smooth waves merge into a richer reality that defies simple intuition. Gibbs Paradox. Imagine two identical containers of gas separated by a removable wall. If you remove the wall and let the gases mix, you expect the disorder or entropy to increase, because mixing different gases always creates more entropy. But if the two gases are exactly the same, nothing seems to change when they mix, so there should be no increase in disorder. Yet classical thermodynamics predicts the same jump in entropy whether the gases are identical or different, which makes no sense. This puzzle was first noted by the American scientist J. Willard Gibbs in the late 1800s when he studied the thermodynamics of mixing. He saw that treating gas particles as distinguishable led to an unphysical entropy increase even when mixing identical gases. The resolution came with the development of statistical mechanics and quantum theory. Physicists realized that identical particles cannot be labeled or tracked. They are truly undistinguishable. When you account for indistinguishability, the extra entropy term drops out exactly for identical gases, restoring consistency. Gibbs paradox teaches us that at the microscopic level, particles are not little billiard balls with name tags, but indistinguishable entities described by quantum mechanics. It shows how careful reasoning about counting states and the nature of particles keeps our descriptions of heat and disorder authentic and free of contradictions. Ultraviolet catastrophe. Imagine heating a metal object until it glows, first red, then orange, white, and finally bluish. Classical physics in the late 19th century tried to predict how much light at each color a hot object emits. Using the laws of electromagnetism and statistics, physicists calculated that as the color shifts toward violet and beyond, the emitted energy should grow without limit, meaning a simple heated object would blast out infinite energy at ultraviolet wavelengths. This clear prediction of infinite light at high frequencies was so absurd that it became known as the ultraviolet catastrophe. The problem arose because classical theories treated light as continuous waves and assumed energy could be shared in any amount. In 1900, Max Planck proposed a radical idea to rescue physics. Energy is exchanged in tiny packets, or quanta, with size proportional to the light's frequency. By assuming each vibrating atom in a hot object could only emit or absorb whole quanta, Planck's formula matched experimental observations perfectly and prevented the runaway energy at ultraviolet colors. Planck's solution launched quantum theory, leading Einstein to explain the photoelectric effect in 1905 and the full development of quantum mechanics in the 1920s. The ultraviolet catastrophe reminds us that sometimes the smallest things, discrete packets of energy, upend grand continuous views of nature, and that genuine progress can come from questioning the most basic assumption. Ehrenfest Paradox. Imagine a perfectly rigid circular disk spinning faster and faster. According to Einstein's theory of relativity, objects in motion contract along the direction of motion. Points on the rim move fastest, so the rim should contract, while the center does not move and stays the same size. This suggests the circumference shrinks, but the radius remains constant, which breaks the usual relation between a circle's radius and its circumference. This puzzle was posed by Austrian physicist Paul Ehrenfest in 1909 to highlight tensions between rigid bodies and relativity. In everyday life, wheels and disks seem solid and unchanging, but relativity shows that no perfectly rigid object can exist. Signals to keep it rigid would have to move faster than light. When a real disk spins, internal stresses build up and it deforms rather than maintaining perfect shape. Modern treatments use non-Euclidean geometry to describe the spin disk's distorted space. The circumference measured by observers at rest is different from the one measured by someone riding on the rim. Ehrenfest Paradox teaches us that moving frames can change the very geometry of objects, and that our simple ideas about shapes must adapt when speeds approach that of light. As you imagine the disk slowing to a gentle turn, feel your mind unwind and settle ever more softly. Poincaré Recurrence. Imagine a box filled with gas molecules moving in all directions, bouncing off the walls and each other. Poincaré's theorem, proved by Henri Poincaré in 1890, says that given enough time, the system will return arbitrarily close to its initial state. In other words, after a very long period, the exact arrangement of molecules you started with will almost reappear. This seems astonishing because we expect systems to move toward disorder and equilibrium, never back to their precise starting condition. Yet the theorem applies to any system governed by fixed energy and confined to a finite space, showing that microscopic dynamics can, in principle, retrace themselves. The paradox lies in the astronomical timescales involved. For even a tiny amount of gas, the time required exceeds the age of the universe by many orders of magnitude. So we never actually observe these recurrences. Still, Poincaré Recurrence reveals that the second law of thermodynamics, entropy increase, is statistical rather than absolute. It underscores that while disorder is overwhelmingly likely, exact reversions remain a mathematical possibility. Poincaré recurrence deepens our understanding of how certainty in fundamental laws coexists with practical irreversibility in the world we see. It shows that authenticity in physics comes from recognizing both what is possible in principle and what is effectively impossible in practice. Fermi Paradox. Imagine looking up at the night sky and wondering, with hundreds of billions of stars in our galaxy alone, many similar to the Sun, each potentially hosting planets capable of life. Simple estimates suggest life should be common, and reach technological stages far older than ours. Yet we see no clear signs of extraterrestrial civilizations, no signals, no artifacts, no evidence of vast interstellar engineering. This mismatch between high probability estimates and the complete lack of observations is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunchtime discussion in 1950. He pointed out that even if just one civilization developed a spacefaring technology a few million years before us, it could colonize the galaxy on timescales far shorter than the galaxy's age. Over the decades, scientists and thinkers have proposed many explanations. Perhaps intelligent life is extremely rare, with Earth as a unique outlier. Maybe advanced civilizations self-destruct before achieving interstellar travel. It is also possible that we are deliberately isolated or observed silently by more advanced beings who choose not to interfere. Some suggest that signals and probes are already here but go unrecognized, or that the vast distances and limitations of physics make communication effectively impossible. The Fermi paradox remains authentic and deeply informative because it forces us to examine our assumptions about life, technology, and the nature of the universe. It combines simple probability arguments with observations or lack of them to pose a profound question: are we truly alone? Or is the silence itself a message about the challenges of surviving and communicating across cosmic distances? This puzzle continues to guide research in astronomy, biology, and even philosophy as we search for answers among the stars. Observer effect. Imagine trying to measure the position of a tiny particle like an electron. To see it, you must shine light on it. But light is made of photons that carry energy. When a photon hits the electron, it knocks the electron off course. In other words, the very act of observing or measuring the particle changes its behavior. This idea was first noted in early 20th century physics as scientists studied atoms and electrons. In classical physics, you could measure the speed of a car with a radar gun without affecting the car. But at atomic scales, the tools we use to look become part of the system. Heisenberg's uncertainty principle from 1927 formalized this by showing that the more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. In practical terms, the observer effect appears in everyday devices too. Electron microscopes use electrons instead of light to image tiny structures, but those electrons can alter or damage delicate samples. In quantum computing, reading a qubit state destroys the superposition that carries information. The observer effect teaches us that measurement and reality are inseparable at small scales. It reminds us that authenticity in physics means accounting for the influence of our tools and methods, and that uncovering nature's secrets often requires understanding how our own actions shape the results. Quantum Zeno effect. Imagine you have a radioactive atom that normally decays after a certain time. Now suppose you check on it very, very frequently, so often that each time you look, it seems not to have decayed yet. Quantum theory shows that if you measure a system continuously, you can effectively freeze its evolution. In simple words, a watched pot never boils. This effect was named in 1977 by physicist George Sudarshan and by Dhyanath Misra. They showed that rapid, repeated observations collapse the atom's quantum state back to its original form, preventing it from changing. Experiments with unstable particles and trapped ions have confirmed that frequent measurements slow or stop decay and other quantum processes. The quantum Zeno effect highlights how the act of observation is not passive at the quantum scale. Rather than just revealing what's there, each measurement actively reshapes the system's evolution. It underscores the deep link between information gathering and physical behavior, showing that knowing too much, too often, can literally hold nature in place. Thomson's lamp. Imagine a lamp with a switch that you flip on and off in ever shorter intervals. You start at time 0 by turning it on after half a minute, then off after a quarter minute, then on after an eighth, off after a 16th, and so on. After one full minute of doing this infinitely many times, is the lamp on or off? This paradox was introduced by the mathematician and physicist James Thomson in 1954 to illustrate a super task performing infinitely many actions in a finite time. In everyday life, you might flip a switch a few times and clearly see the lamp's final state. But this thought experiment asks what happens when the number of flips becomes endless, with each taking half as long as the one before. No matter how you try to decide, you end up with a contradiction. If you assume the lamp ends on the last action, there is no last flip because the sequence never ends. If you try to pair flips, each on is matched by an off, suggesting the lamp should be off, yet neither reasoning holds when you truly reach 1 minute, since the infinite series of flips has no final member. Physicists and philosophers have debated its resolution. Some say that true supertasks cannot exist in the physical world because real processes have limits, atoms take time to change state, switches have inertia, and energy costs prevent infinitely fast flipping. Others explore mathematical frameworks where the lamp's state is simply undefined at the limit. Thomson's lamp highlights how infinity can challenge our assumptions about time and action. It remains an authentic puzzle in the study of infinity, motion, and the foundations of mathematics and physics, reminding us that pushing familiar operations to their extremes can uncover deep questions about what completion truly means. Hilbert's Hotel. Imagine a magical hotel with an infinite number of rooms, each numbered 1, 2, 3, and so on, all the way to infinity. One night, every room is occupied by a guest, so the hotel is full. Now, a new guest arrives and wants a room. In any normal hotel, you would say, "Sorry, we're full." But at Hilbert's Hotel, the manager simply asks every guest in room 1 to move to room 2, every guest in room 2 to move to room 3, and so on forever. Room 1 becomes free and the new guest checks in. This seems impossible because you start with no empty rooms, yet by shifting each guest one room higher, you create exactly one vacancy at the start. Even stranger, if a bus with infinitely new guests pulls up, the manager can move the person in room 1 to room 2, room 2 to room 4, room 3 to room 6, and in general, move the guest in room N to room 2N. That frees up all odd numbered rooms, infinitely many vacancies, to accommodate infinitely many newcomers. David Hilbert introduced this thought experiment around 1924 to show how infinity defies our everyday ideas of full and empty. It illustrates that infinite sets can be put into one-to-one correspondence with proper subsets of themselves. Hilbert's Hotel helps clarify topics such as set theory, the nature of infinite series, and the foundations of mathematics. It also appears in discussions of cosmology, where some theories propose that space itself might be infinite in extent. While no real hotel could implement these infinite moves, Hilbert's hotel remains an authentic and deeply informative illustration of how infinity stretches logic. It reminds us that when dealing with the infinite, our intuitive rules about counting, filling, and capacity no longer apply in the familiar way. Boltzmann Brain. Imagine a single brain forming for a brief moment out of random fluctuations in a sea of particles, complete with memories, thoughts, and awareness before it dissolves again. According to some interpretations of statistical mechanics and cosmology, if the universe lasts long enough and has enough random particle motion, such a Boltzmann brain is more likely to pop into existence briefly than an entire orderly universe emerging as we see it. This idea traces back to Ludwig Boltzmann in the late 1800s, who explained that systems tend toward more probable disordered states. In the 1970s and 80s, physicists like Richard Feynman and Stephen Hawking realized that in an infinite or extremely long-lived universe, random fluctuations could produce any configuration, including a single conscious brain, complete with false memories. Statistically, there could be vastly more Boltzmann brains than naturally evolved beings. The paradox is unsettling. If most observers are Boltzmann brains, then our own experiences and memories become unreliable. Perhaps we are just brief fluctuations with no real past. To avoid this, cosmologists require models of the universe that suppress such fluctuations or end before Boltzmann brains dominate. Proposed solutions include a universe that decays after a finite time, or one in which the dark energy driving expansion changes over time. Boltzmann brain forces us to examine our assumptions about probability, time, and what it means to be an observer. It connects deep ideas from 19th century thermodynamics with modern theories of cosmology, ensuring that our picture of the universe remains both authentic and consistent with the fact that we remember a coherent past rather than just random noise. Wheeler's delayed choice. Imagine sending a single photon toward a device that can either detect it as a particle or let it interfere with itself like a wave. You decide whether to insert or remove the final beam splitter only after the photon has passed the first splitter, but before it reaches the second. If the beam splitter is in place, the photon creates an interference pattern, behaving like a wave. If it is removed, you detect which path it took as if it were a particle. Remarkably, the photon's earlier behavior, wave or particle, seems to depend on your later choice. Physicist John Wheeler proposed this thought experiment in 1978 to probe the nature of quantum measurement. It suggests that quantum objects do not decide on wave or particle behavior until the moment of measurement, and that this decision can be influenced by choices made after they've entered the apparatus. This challenges classical ideas of causality in time because it feels as if the future measurement reaches back and determines the photon's past. Like Alain Aspect's group in Paris and Anton Zeilinger's team in Vienna implemented delayed choice setups, confirming Wheeler's predictions. More recent quantum eraser experiments showed that even information erased after detection can change, whether information appears further emphasizing the role of measurement and information in defining reality. Wheeler's delayed choice remains authentic and deeply informative because it rests on clear experimental tests rather than mere speculation. It highlights that in quantum mechanics, the boundary between past and future blurs, and reality only crystallizes when we actively measure it. By grounding the paradox in real laboratory achievements, we see how foundational questions about time, causality, and observation drive ongoing research into the quantum world.